Hello everyone, am I audible? Can anybody unmute and just tell am I audible? Oh, okay, yeah, thanks. So I will keep admitting everyone as they come. Yeah, we will start in a couple of minutes because many people are just joining, so I have to admit them alongside. Yeah, so I have activated that now, Balaji. So I think we'll start now, and I will keep admitting everybody as they come. So good evening, everyone. Welcome to the problem-solving session for the NPTEL course Introduction to Robotics. I think that you had another session before this, right? From 4 to 5 p.m. Anyone? Hello?
No, no, sir. This is our first session in this particular course.
Okay, okay. Yeah, it's fine then. So I hope you all have went through week one lectures, right?
Yes, sir.
Yeah.
Yes, sir.
So the main purpose of these sessions is to clear first of all your doubts that you might have while watching the lectures, and also to solve some problems with you related to the concepts that you learn in the lectures. So I'll start with introducing myself. So I am Nimesh. My name is Nimesh Kandelwal. I did my bachelor's in mechanical engineering from MNIT Jaipur, and I graduated in 2020. And after graduating, I joined as a PhD student in the mechanical engineering department at IIT Kanpur, where I currently pursue my research work. And my some research interests are robot dynamics and control, and stability analysis for legged systems. This is my current area of research actually, and contact force modeling for multi-body systems. So how these lectures or these sessions will work is I will solve some problems here in the live session, and then after each problem, you guys can ask questions related to that particular problem first, after each problem. And then at the end, I will ask more general doubts, some conceptual doubt or any doubt related to the course, of course, that you might have, so that we can discuss at the end. Is that good?
Yes, sir. It is
Yes,
clear.
sir.
Okay. So let us move to the first problem then. Yeah, can you guys see the first problem?
Yes, sir.
Okay.
Yes,
So
sir.
yeah, so the problem says that there is a frame, and what is a frame actually? I think that sir has explained it in lectures quite well. What actually is a frame? Um, so it has some coordinate axes E1, E2, and E3, and it is rotated by some angles. Like given this case, it is first rotated 90 degrees about the E1 axis, and then after that, the rotated frame of the E3 axis of that frame, okay, in you can also say Z axis of the rotated frame, about that we give it a rotation of 180 degrees. Okay, so we want to know what is the final rotation matrix for the after the second rotation that we give. Okay, so I'll do one thing. I'll share my whole screen so that you guys can also see the when I write. Yeah, entire screen. Share. Nice. Okay, and we can open this here. Okay, you guys got the problem, right? It is quite small right now in the screen. Can I hear a yes or a no?
Yes, sir. It is small.
Okay. So what I'll do is I'll start with drawing the frame. Okay. So let us say that this is frame A. I will use the partly is italicized letters for denoting frames. Okay. And let us call the origin here as the letter A. And now this is your even hat, the first axis E2 hat, let's say, no, this is E3, and then you make E2 here. Okay, this is the right-handed coordinate system. Now, and to write this properly as a frame, okay, what you do is you write the origin first. Okay, in this example, we have taken A to denote the origin, and then you write the basis vectors or the coordinate axis, whatever you want to call them. I call them the basis vectors in this fashion. Okay, so now this A is our coordinate frame A. Okay, so here what we have done is first we have given it a rotation about which axis? Even axis. Okay, by what angle? 90 degrees, or I can write pi by 2. Okay, so after this rotation I can say that I have a new frame now. Okay, rotation about even axis. Okay, so the origin of this frame will be the same, but now the basis vectors, or okay, they will be different, right? Some of them might be the same. For example, since we are rotating about E1, so E1 will be the same for this as well as the rotated frame, but you can see, right, in this case when I rotate about E1, this new E2 will be somewhere here and this new E3 will be somewhere here. Okay, of course these are for an arbitrary angle that I'm showing, but here we are rotating by pi by 2. Okay, so I say that these are E3 prime, and now the second rotation I say that I give about this E3 prime axis. Pay attention to this. I'm giving it about E3 prime axis. Okay, this new E3 axis, about this I'm giving the rotation. Okay, not the old E3 axis. Okay, about this I give a rotation of 180 degrees pi. Okay, so after this I get some other frame with the same origin, but now again different basis vectors. Okay, so what I have asked you basically in this question is to find the final rotation matrix. Okay, basically to club both of these rotations, one this and one this, into a single operation to go from A to A double prime. Do you get that? This is the italicized A. Okay, this is the frame A. Is the problem clear?
Yes, sir.
Yes, sir.
Okay. And now how we do that is actually, you might have learnt in the lectures that the final composite rotation matrix is given as the first rotation, let's say, I call it R1, okay, because it is about the even axis, and it is pi by 2. And now since the next rotation is about the new axis, okay, the axis of the rotated frame, okay, basically this body, if I call this body, and if I call this initial frame as the ground frame, okay, then since the next rotation is about the body frame, then I post multiply. Okay, and if I had given in this question that this second rotation is about the initially 3 axis, okay, then what would I have done? Can somebody tell me?
Pre-multiply.
Yes. And why is that? Why do we do this? Why are there different rules for pre and post multiply?
If it's about a fixed axis,
Yes.
we pre-multiply, and if it's about its own
If you want to
coordinate
transfer it
axis,
another
post
one
multiply.
coordinate system to another.
Yeah, so actually, you see, this is the matrix notation, okay, in which we can post multiply things, okay, but so this is some extra bit of info that I'm trying to give you, is that when you write these quantities in terms of tensor, very general quantities, irrespective of what axis you rotate about, you will always write like this, like pre-multiplication. Okay, the first R1, R2, R3, R4, like this. You'll keep pre-multiplying. But when you are trying to write this tensor form in the matrix form that you actually have studied in the week lectures, then when you know keep every rotations in the ground frame, then you get this only, okay, pre-multiplication form. But when you keep R2 in the body frame, and now this R1 is in ground frame and R2 is in body frame, okay, so when you convert R2 to also ground frame and then you put it here, then you actually get the post multiplication sequence. Okay, so this is just algebra, okay, that you get it as post multiplication when you keep rotating about the new axis, okay, the new basis vectors. But the most fundamental thing basically that comes from algebra is that it it is always pre-multiplied when it is as a tensor. Does that make any sense? If not, then yes, you can remember this, that whenever you rotate about the fixed frame, you pre-multiply, and whenever you rotate about the body frame or the new frame, you post multiply. Okay, so in this case, okay, so it is R1. So we know that you guys all know the elementary rotation matrices, right? Or do I have to write them now? If somebody does not know, then they can please speak up.
Sir, I don't know.
Yes. I've also, I don't have a basic concept idea on it, sir.
Okay, okay, okay. I'll tell the basic fundamental rotation matrices itself first. Okay, and then I will solve this question. So what are the fundamental rotation is? If I rotate about the x-axis, okay, if I have a frame, okay, I will take x, y, z. You guys can take f1, f2, f3, or even v2, e3. It does not matter that much. What matters is the concept. Okay, if I rotate about the x-axis by some angle theta, okay, so the rotation matrix for that rotation, okay, for that transformation is given by this cos theta minus, yes, does anybody want to say anything? Okay, no.
Sir, can you please visualize how this came?
uh, Actually, see, you don't need to, you can visualize using a 2D approach, and you can also get this from the Rodrigues formula. Do you know about the Rodrigues formula?
No, sir.
Okay, so let us visualize how this came from 2D approach first. Okay, approach 1. We'll go into 2D for this, okay, first. So this is x and this is y. Okay, and let us say I wrote, and z is out of this plane. Okay, this is z. That I have not drawn here because this is 2D. Okay, now I rotate this complete frame about, these, no, you do not rotate frames actually, it will confuse you right now. Okay, so let us say there is a vector v, okay, in this frame, and then you rotate this vector v by some angle theta, and you get v prime in the same frame, right? Okay.
Yes, sir.
Yeah. So can you tell me, and let us call the coordinates as x and y, and call the coordinates of e prime as x prime and y prime. So you guys all know this from your high school geometry. So can you give me the expressions for x prime and y prime in terms of previous x and y and theta? Anyone? So you can do this on your own also, but what you will get, because this is algebra, this will only eat up in the time for the other problems. Okay, so what you will get is this. Is there any doubt in this, how this came?
Yes, sir. Can you please explain?
Okay. See, I will tell you the procedure, okay, that you can follow to get this, because it is just, seriously, it is just algebra. You have to just take projections here, and then you have to equate them. Okay, this x prime, because let's say that this length, okay, is x prime cos theta plus alpha, okay, and this length then becomes y prime, this is the same length L of this vector, and this is actually x prime, and this y prime is the same L times sine theta plus alpha, okay, and then you do the same for this, okay, because this will also come in terms of L, right? So now when you, do you get this? L cos alpha and ys L sin alpha, right? And now when you open this, okay, let me do this. Let us see. L cos theta cos alpha. I hope I do not need to tell that how this also comes. And y prime is L sin theta cos alpha minus cos theta sin alpha. Is that fine?
Yes, sir.
Yes, sir. I know that comes from a basic trigonometric formula.
Yes, yeah. So if you see that you have L cos alpha here and L sin alpha here, and the same L cos alpha and L sin alpha. Okay, so when you substitute this x and y as L cos alpha and L sin alpha in place of L cos alpha and x alpha, you will directly get this. This is x cos theta minus y sin theta, and y prime becomes sin theta, right? X sin theta plus, this will be plus because it is sin theta plus alpha. You guys can correct me, okay, if I make some mistake like this. So now you agree that we know where this came from?
Yes.
Okay. So now using this, if I want to write it in the matrix form, okay, x prime y prime. Okay, so you just have to factorize this. Okay, so this becomes cos theta minus sin theta and cos theta, and this becomes x and y. This is your basic linear algebra. You are factorizing. You're just factorizing your algebraic equation that you have here. Any problem here?
No, sir.
Good, very good. So you can see that this is the 2D rotation matrix that I got when I rotated about z, right? Rotated about z. Okay. So when I try to write this in 3D, okay, this actually, because since I rotated about z, okay, there will not be any change in the z1, but for the x and y, because if I want to write z here also, let's say z, okay, so to make it consistent, because now there are 3 here and there are 3 here, but since I rotated about z, will the z change? Okay, because z prime has to be equal to z, right? Is there any doubt here?
No, sir.
Okay, so let me write it like this. There are 2 equations, these are the 2 equations, and the final equation is this, z prime equal to z, right? And here also it is 0 times z plus 0 times z, right? So when I write this now in the matrix form, okay, for 3D rotation, for 3, for 3D vectors, x prime, y prime, z prime, okay, you will get the same thing that I was telling you, minus sine theta and then 0, because 0 times z, and then this becomes sine theta cosine theta 0, because for y also it was 0 times z, and then for z prime it was 0 times x plus 0 times y plus 1 times z, right? And then multiplied by what here, no, not x prime, x, y and z, the original x, y and z. Is that fine?
Yes, sir.
So this is the fundamental rotation matrix about z, okay. This is what we call the fundamental rotation matrix for a single rotation, okay. So cos theta minus sine theta 0, sine theta cos theta 0, okay. Now the similar treatment if you do for the other 2 axes, okay, you rotate about x, not z, x, okay. So let's say you rotate about x, okay, and then you watch the rotations how they happen in the yz plane, okay, then this matrix will come out as something similar, okay. Just the positions have changed. You guys are able to understand my handwriting, right?
Yes, sir.
Yes, sir.
Yes, sir. That's not a big problem also.
Okay, okay. Okay, and for the y, okay, when you are you can derive it, it will come out, but yeah, there will be a slight change here when you are deriving it, okay, in the pattern if you want to see, okay. So there will be plus sine theta here, okay, in the third term, okay, and this second one will be this, and then this one will be minus sine theta about for rotation about y. Is that fine? You can try to derive, you rotate about y and then you watch rotations in the xz plane, it will come out to be like this. Is this fine?
Yes, sir.
Okay, so now everybody knows about fundamental rotation matrices, right?
Yes, sir.
Yes, sir.
Yes.
Okay, so now we will go back to the original question, okay, that okay, this you can remind me if we have time at the end of the session that I need to tell the approach 2 for this also, okay. Yeah, so yeah, we were here that the final rotation matrix for our current problem will come like this, okay. And why did we post multiply here instead of pre-multiply? We have also discussed this because this rotation, this second rotation is about the new axis, okay. So what we have here is r is r1 pi by 2 and r3 pi. This 1 and 3 is actually I'm using them in substitute of x and z, okay. So I don't think that is that big of a problem. Okay. So can somebody tell me what will be the other terms for this one? The first one.
1,
0.
1, 0.
Okay. What will be here?
Cos 90.
Yeah, you have to evaluate cos 90.
1.
0.
Yes. Okay, so it will be cos 90 here. That is 0 because Rx has cos theta here, right? So this is 0. And what will be here? This entry?
Minus 1.
Minus 1.
Minus.
And here?
1 0.
Yes. Okay, so this one is 1. And this is 0. And can you tell me similarly quickly for R3? I will write the easier terms by myself. You tell me the other terms. So what will be the 0 0 term?
Minus 1.
Minus 1. Right. And
0.
this will be 0. And here?
0.
And
0. Minus 1.
Minus 1.
yeah.
1 0 1 1.
No, it is, yeah. So I have already written the last one. Okay, so now you just multiply these two and you will get your final rotation matrix. Okay, so what will you get if you multiply this? Minus 1, 0, 0, then 0, 0, minus 1, and then 0, minus 1, 0. I have just multiplied these two matrices here. Is there any problem?
No, sir.
No, sir. No, sir.
Okay. Now we have got the final rotation matrix. Okay, but always keep that in mind when you're writing all these matrices using the conventions that you have been either taught or are written in the book. Okay, these rotation matrix give you the rotation from body frame to the ground frame. Okay, what I mean by from body frame to the ground frame is that
Excuse me, sir.
yes,
Actually, sir, since A B matrix multiplication is not same as B A matrix multiplication,
yes,
so which order should I follow?
yes, I'm telling you, no, we did post multiplication here. And why did we did post multiplication? Because the next rotation, the second rotation that I gave was about the new E3
New.
axis, right?
Actually, sir, your voice is lagging, so I am unable to hear you clearly.
Okay, okay, can you hear me now?
Yes, sir.
Yeah, so we pre-multiply. Okay, we would have done R3 times R1 if this rotation about 3 was about the original E3 axis. Okay, but this is not the case here. We did R1 and then we post multiplied this R3 because this R3 was about the new E3 axis. Okay, so this is how you decide if you have to pre-multiply or post-multiply. Did you get it?
Okay, sir.
Okay, cool. So this is the final rotation matrix, but yes, a word of caution. Be wary of from what frame to what frame, you're taking your quantities to. Basically, when you are using this matrix, okay, you will always be writing, using it like this, that you have some vector that is expressed in frame B. So you multiply it by this RBG, and that is, multiplying this gives you this vector as seen in frame G. Does that make sense? Yes or no? You can say no. I will tell.
Yes, sir.
No, sir.
Okay. Okay. So, what if I want, this I have in ground frame and I want in body frame? What do I do then? What do I multiply here?
Inverse.
Yes.
Inverse.
Okay. So the inverse of the same thing. Okay. I can just invert this thing here, right? Okay. But what is the inverse of a rotation matrix?
Transpose of it.
Yeah,
R2.
transpose itself. Okay, you know how this came about, right? Why is the inverse the transpose?
Because when they are orthonormal two frames, then we take it our inverse as equal to transpose of it.
Yes. Okay. Exactly. So since you have this, there is this property also that they follow. Okay. R transpose R equals to the identity. Okay, and also there is this property that the determinant of R, okay, it is what? Determinant of a rotation matrix is equal to what? Can somebody say? Is the meeting on?
Yes, sir, it is on.
Yeah, so what do you guys know what is the determinant of a rotation matrix? Okay, I will tell you, don't worry. You can say that you don't know. Okay, so the determinant of a rotation matrix is always +1. Okay, so see, we say that the rotation matrix is an orthonormal matrix, but that is incomplete. Rotation matrix is a special orthonormal matrix. Okay, because for if R was just an orthonormal matrix, then its determinant can be +or -1, right? But for rotation matrices, we choose rotation matrices to be such that it is only +1. Okay, you might have seen in some textbooks that this R, your rotation matrix belongs to the SO3 group. Have you seen that? Yeah, yes or no?
No, sir.
No, sir.
No? Okay. So
No, sir.
yeah, you will see when the course progresses. Okay. So SO3, like you have seen R3, right? Do you know what is R3?
3D space.
3D space, exactly. Okay, so it is a set of all real number of basically it is a a set of 3 real lines orthogonal to each other. Okay, so this SO3 is actually a subset. No, so similar to that, it is not a subset of R3. I should not say this. Okay, so this SO3 is a group of matrices whose determinant is +1. Okay, orthonormal matrices whose determinant is +1. Okay, so this is just some extra bit that you can use sometime in your career. So yeah, is this question clear? And about how these rotations work? Can I get a yes or a no?
Yes, sir.
Okay.
Yes, sir.
Then what we will do is we will go on to the next question. Okay. So can you guys all see the question?
Yes, sir.
Yes, sir.
Okay, so this problem, I will just read it out. A robot arm attached to the ground takes an object from 110 to 232 and in doing so rotates it with respect to the ground frame by the following XYZ angles 90, 180 and 60 degrees. So we want to know the final homogeneous transformation matrix for the object. So do you guys know what is homogeneous transformation matrix?
4D transformation, 4x4 matrices.
Yes. Okay. So it is a transformation basically in which you have clubbed both the rotation and the translation in a same matrix. Okay. Is there any doubt in that? Because if you have any doubt in this homogeneous transformation matrix, then you should watch the lecture again because it is explained there. Okay. So problem number 2 is what we'll discuss now. Okay. So what I have given in that is there is an object. Okay, let us say this. There are more people coming. Okay, so initially it is at what coordinate? Yes, you can say. Finally, I have put it at what?
232.
Yes. 2, 3 and 2. Okay. But I have not just put it here. I have rotated it also. Okay. And what did I say? How have I rotated it?
90, 180 and 60.
Yes. So, a word of advice here. Whenever you have been given a set of angles, rotation angles like this, always be sure that you know about which axis these angles are given. Okay, because in this question, if you can see, I have given it explicitly that these are with respect to the fixed ground frame. Okay. Yeah, can I get a yes?
Yes, sir. That's
Yes,
understandable.
sir.
Yes. So what does that mean? Okay, this xyz by convention it means that I'm first rotating about x by the specified angle, and then I'm rotating about y by the specified angle, and then I'm rotating about z by the specified angle. And since it is about all the fixed axis, I've specified this in the question. So the final rotation matrix will be, how will it be written? Will I post multiply everything or pre multiply?
Pre-multiply.
Pre-multiply.
Yes. Okay, so it is rotation about 1, or I can write x also, by 90 degrees, then a rotation about y 180 degrees, and then a rotation about z 60 degrees. Okay, this is the rotation. Okay, and I'm not coming to the translation part because that is the easier part. I think you all can do that. So we'll do, handle the rotation first. So I think once we have figured out, everything that about what axis these are given and what the values are, and should we post multiply or pre multiply, the rotation is also pretty much done. Now it is just mechanical. You have to put the values and multiply. Okay, so I will try to do slightly fast for you guys so that I can tell you more. Okay, so if you guys have any doubt in how I'm writing these values, you can stop me and ask. Okay, and ry 180 so 0 0 1, 0 and 0 here also, and then about x 90 degrees, so it becomes -1 0 1 0 0 0. Is there any problem in this?
No, sir.
Okay,
No, sir.
if anybody has any problem, they can say. Okay, so what I will do is I'll write it like this. This denotes that this is the same, and then I'll multiply these two first. Okay, so yeah, multiplying it, it is just calculation. Okay, I am sure you can do that by yourself. And now we'll multiply this by this because it is now pre-multiplied here. Okay, so what do we get? Can anybody tell what will be the 0 0 term?
-1 by
Minus
2.
1 by 2.
The second, in the same column, second term?
Minus minus root 3 by 2.
Yes, and the third?
0.
0.
Similarly, can you very quickly tell me this about the second one? Second column?
0.
0. Yes. 0.
0.
0.
And
-1 by 2.
Minus 1
the
by
next
2.
column?
0.
What 0? Root 3 by 2. Do you see how it is root 3 by 2? Hello, am I audible?
Yes, sir. You're audible.
Yeah, okay. So now I'm multiplying this column
With this
by
column.
this row. Okay. So when I multiply these, I get root 3 by 2. Is there any doubt here?
No, sir.
Okay. And the second thing will be minus half. And the third, 0.
0.
0.
So this is your final rotation matrix. Okay. But this is not the homogeneous rotation matrix. What do I have to do?
Excuse me, sir.
Yes?
Sir, in the second row,
Hmm.
the first part is the first matrix is missing, right? The first matrix is formed by multiplying the first two matrices, right?
Yeah. So see, this matrix is a multiplication of these two. Okay, and actually my voice might have broken because I just used this to substitute this matrix here, so that I did not have to write it completely. I was just making my life easier.
Oh, okay, sir.
Is that fine now?
Yes, sir. Yes.
Okay. So see, we have already gotten, the final notation matrix. So, and can you tell me the translation part? Yes. Because I am taking it from 110 to 232. So what will be the translation? So it will be, it is initial, 0.1 minus, where did it go? Yeah, 0.2. So yes, okay. 1, 2, 2.
Two.
Okay, so now I have everything that I need to write my final homogeneous transformation matrix actually. This T is quite big. Yeah, T. Okay, so what is the form of T? You guys know?
Or
First protection matrix.
first rotation and then translation.
Yes. Rotation, translation, and there is a scaling factor here. And that in
1.
robotics, we use 1 for convenience. And then the perspective vector, we use, a zero row vector. Okay. So now if I combine everything that we have calculated above, then I think we can write it very simply. Root 3 by 2, 0, 0. And you see, since to calculate, the rotation matrix, we have to multiply all these matrices. Okay, we have to multiply various matrices. Here it is only 3, but there might be some, question that you might be doing where you have to multiply 6, 7 matrix. So after all that multiplication, how do you check if you have not made any mistake?
We will just go for the graphical approach, like we will first find out how much it translates, and then we will move for the angles it had covered.
Actually, see, graphical approach does not work very well when you have more number of frames. Okay, so a very easy check is that,
Try an origin approach. Maybe the easiest point origin is matching or not.
um, so there is a see, currently I'm talking only about the rotation part. Okay.
Okay.
Yeah. So how do because we are having to multiply all these matrices to get correct rotation, right? First of all, initially.
Sir, your voice is lagging. Can you please repeat?
Oh, okay. So what I was saying is that currently I am talking only about rotation matrix. How do you check that this rotation matrix, the multiplication basically that you have done, is correct? Vidyadhar, are you trying to say something? Your voice is not clear at all. I think you need to fix your mic. Vidyadhar, can you mute? It is only static actually, we cannot hear, and it is disturbing others. Thank you. Okay, so the first check that you can do is you can try to check the determinant of R, because we know that it should be +1, and if it is not +1, then of course we have made some mistake here. And after that, you can check that each column vector or each row vector, any of them, what should be the norm of these vectors? Okay, or what should be the length of each column vector or each row vector?
3 by 3?
No, that length should be 1.
1.
Okay, because I think I should tell you guys this also, that this question is done at this point. Okay, so I will just tell you that this rotation matrix that I have got initially, I will write it again because it is fairly important what I am about to tell you. 3 by 2 minus half and 0. Okay, so the I have told you, right, that this is from the body frame, basically as in ground frame. Okay, so what this matrix is actually, these column vectors are the basis vectors of frame B, as seen in frame G. Does that make any sense? Anyone?
Is it like B's coordinate system represented in G's unit vectors?
Yes, exactly.
Oh.
Okay, so this actually is even prime, and this is
Okay.
E2 prime, and this is E3 prime. Okay, but all of them have been represented in G system.
Okay. Yeah.
Okay, and if I write them in B system, okay, then they will simply be this unity.
1 0 0 0 1.
Okay, and then of course 0 1 0, and then 0 0 1. Okay, this is E2 prime as seen in body frame. Okay, because you can verify it here also. If I want rotation from my body in the same body, what should be the rotation? None. So basically identity. Is there any problem here? Any doubt?
Excuse me, sir.
Yes.
Sir, about for like 2 minutes, I lost my internet connection and I was not able to listen to what you said. Can you please repeat what you said?
Sure. Yeah. So what I was telling, can you hear me now? Venkatesh?
Yes, sir. Yes, sir.
Yeah, Venkatakrishnan, sorry. Yeah. So what I was saying is, these column vectors of the rotation matrix are the basis vectors of the rotated frame as seen in the ground frame. Does that make any sense?
Yes, sir.
Yeah, so that is all I told, because I was just after that telling that if you try to write these same vectors in their own frame, okay, then of course you should get unity. Okay, but if you are writing these rotated basis vectors as in the ground vectors, and if you stack them as like this as column vectors, the matrix that you get is actually the rotation matrix from B to G.
Yes, sir.
Okay, and now similarly, if you so you can check it on your own that the row vectors, okay, of this matrix, okay, these are the basis vectors of the initial frame as seen in body frame. Okay.
Yes, sir.
Okay, you can check. I am just telling you this. Okay, that column vectors, and this is the reason why just taking a transpose is comes out to be equivalent as the inverse. This is actually a result of that, not vice versa. Okay. Okay, is there any doubt here? Yes, anybody has a doubt?
No, sir.
Okay. So I think we have more than 10 minutes. We can do one more question. Okay, so yeah, can everybody see the question?
Yes, sir. That is the more clearly visible.
Yeah. So actually this is the same transformation matrix that we have got in the previous question, and now we want to know what is the inverse of this transformation matrix. Okay. I will admit people. Yeah. So you guys got the question, right?
Yes, sir.
Yeah. So we will try to do something here. Shit. Okay, whatever. We'll write it again.
Sir, I have one doubt.
Yes, you can ask.
Sir, why to take a ground matrix, sir?
Ground matrix?
Yes, sir.
Ground matrix, or do you want to say ground frame?
Ground frame, sir.
Yes, okay, because first of all, see, when you are trying to do dynamics, at the end of the day, you want to be able to apply Newton's laws there, right?
Yes, sir.
And can you tell me Newton's laws are valid only for what kind of frames?
Inertial frame.
Inertial frames, exactly. Okay, so this ground frame that we draw at the starting, okay, okay, we can draw it like, we can show that this is grounded. Okay, we assume that there is a grounded frame, and that we
Yes.
assume is the inertial frame for our whole setup. And in this frame, after doing all the kinematics and when we arrive at dynamics, in this frame we apply Newton's laws because they are valid only in this frame.
Okay, sir.
Okay.
Okay, sir.
Sir, what is use of this matrices in robotics?
Oh, they. Okay. What is the use of all matrices, or what is the use of specifically the transformation
What?
matrix?
All matrices, man.
All matrix. It is actually just easier to use them as a matrix. Okay, because have you done any course on linear algebra?
No, sir.
Okay. Can I know which year you are in?
Sir, Rajasthan.
No, which year? Like, are you in college?
Oh, college, sir. Actually, Rajasthan,
No, no, no.
JNU.
I am asking,
Alright.
are you in college?
Ah,
Okay.
yes, sir.
In college, in which year are you in?
Second year.
Second year. Then you might have studied linear algebra in your first year mathematics, right?
Sir, I am doing BCA.
Okay, okay. Okay, I'll just quickly go over why we, use matrices. Because
Thank you,
I think Google Meet does not allow me to extend the meeting beyond 1 hour. Okay, let us say I have a system of linear equation. What not? Why is it? 4y plus 2z equal to, let's say, 0. This is a random system that I'm taking. Okay, this is y plus z is, this is all. Let us take this also 0. And 7x plus 8y plus 10z equals, let's say, 13. This is a random, system of equations that I've taken. Have you seen this somewhere before? Who was asking, Satya?
Yes, sir. Yes, sir.
Yes, sir.
How did you previously solve these kind of equation? What we used to do is that we used to eliminate all these, right? You multiply,
sir.
let us say
Yes,
By
sir.
keeping a 3 into 3 matrix, we can solve it, sir.
Yeah, no, I'm actually, he was asking what is the motivation of arranging them as matrix, because he does not know that before.
Okay, sir.
Yeah. Okay. So Satyam, are you there?
Yes, sir.
Yeah. Okay. So what you can do is you can either, multiply this second equation by 3 and subtract from the first equation. Okay. And then we, just keep eliminating things like this to get the values of x, y, and z, right?
Yes, sir.
This you might have done in 12th, right?
Yes, sir.
Okay. So now that is one way to solve. Okay. But the more convenient way to solve it, okay, is, you arrange it as a matrix. Okay. And why arrange it as a matrix? Because it makes it smaller also. I will tell you how it makes it smaller. X, y, z equal to 0, 0, and 13. Okay. So now you see I have grouped them as some quantities, right?
Yes, sir.
Okay, so I can now write this as A V equal to B. So now this is much easier to write. And this seems like a single equation,
Yes, sir.
right? And now if I assume that there is a multiplication here, okay, so now I can write V directly as A inverse times B, right? Because
Yes,
if
sir.
I multiply, this equation, I multiply both side A inverse, this becomes A inverse AV is equal to A inverse B, right? And this A inverse times A becomes identity, right?
Yes, sir.
So now I have directly solved this system of equations without having to, do all those eliminations that I was talking about.
Yes, sir.
So this is the motivation of, using matrix method. It is just convenient and it is very powerful actually, because, it makes things simpler for us. Okay.
Yes, sir. Yes, sir.
So I think we should quickly do the third problem. Yeah. So can somebody tell me what the transformation matrix was? Wait, I have it here. Yeah. Minus half 0.
Sir, you were also going to tell the second way. You told that.
Yes. So tell me, do you want to know how to calculate the inverse of this matrix, or do you want to know the second way? If we could do only one, what would you choose?
Inverse is easy, sir. We can go for the second way.
Okay, and it might be easier for you. I'll just tell the motivation of the form of inverse that we chose here. Okay, so I'll try to do it quickly and then tell you about the second way also. Or we can always these will be weekly sessions, so we can always discuss in the next session. Okay, so this T, I have partitioned it like this because we have seen, right, that this is written like this. Any doubt in that? Yes or no?
No, sir.
No doubt, sir.
Okay, so this is also, always remember, like rotation matrix, this is from some frame to some another frame. Okay, but now these just use the homogeneous coordinates. What are homogeneous coordinates? All of you know. Okay, so now if I want to write T, the inverse, okay, so either I can do direct matrix inversion that I was talking about earlier. Okay, but as we all know, there are problems with matrix inversion. Okay, so instead of doing this, what we do is we use we say that we are a bit smarter. Okay, we exploit the structure of the problem. Okay, you might have been told that this inverse is this. Okay, have you all been told this? Yes or no? Hello?
Yes, sir.
Yes, but do you know why this? Yes, anybody? Okay, so I will assume that you guys don't know and then I will tell. Okay, that how does this, the geometrical motivation, how you can convince yourself that this is actually true. Okay, because you should always convince yourself with scientific proofs that things you are doing are actually true and make sense scientifically.
Excuse me, sir.
Yes?
Sir, I was busy, so I couldn't join on time. So, is there any way there's a recording for this?
Yeah, it is being recorded and it will be, uploaded at the course website.
Okay, sir. Thank you so much.
Okay.
Okay.
And let us say that this is the rotated frame. I will try to do it a bit fast because I'm not sure if the meeting will end or it will continue. Well, this is not really a straight line, but let us assume that this is the translation vector from this, ground frame to the body frame. Okay, so basically, when you write T BG, from body to ground, you are writing it as R BG, and this remains the same, the 0, 1 cross 3 vector, and this is the T from G to B, right? This vector from origin of G to origin of B. Is there any doubt?
No.
Okay, so when you are trying to write this as GB, what do you want to write? You want to write R GB and T from B
TG.
to G. Okay, from B to G.
0.
Yeah, and then 0 and 1. Okay, but now if you try to see that initially when I wrote this TGB, about which frame did I write this?
Ground frame.
Yes. Okay, so this TGB was written about ground frame. Okay, and now because all these quantities should be in the same frame when you are writing any vector or matrix or tensor equation. Okay, when you are assigning frames in a single equation, all the quantities should be in a single frame. Okay, so all these are in frame G. So this quantity, since you're writing everything in B frame now, you want this to be in frame B. Okay, but you know that TBG in frame G is actually just minus of GB. Is this right? Yes. Is
Sir.
there any doubt? Yeah. Yes.
Yes, sir. Understood.
Understood, right? Okay. So now I want TBG in B frame, and I have this, TBG in ground frame. What can I do to convert this into this, in B frame? Can anybody say? What should I multiply it with?
Inverse.
I mean, yeah, we'll come to the inverse, but basically,
RBG.
right? This one.
Transformation or
Okay. And now if we see what this actually is, okay, this is just R transpose or the inverse of from B to G, right? And now we'll replace this also, minus T GB. Okay, and now we were calling this RBG as R itself, so we'll say R transpose, negative comes here, and TGB as written in G frame, right? As written in G frame. So this becomes just T, RT. Okay. And also, so I think the meeting can go on, so I will keep it going on. Everybody's there, right?
Yes.
Yeah.
Yes, sir.
Yes, sir.
Okay. So we wanted R GB here and T BG and everything in body frame. Okay. And this we actually got it. We calculated it. Ah shit. This is the body frame. Wait. Somebody has. Yeah. So now we just want to write them in the quantities that we know. So this is the R transpose, and you know that when I write only R, it actually means R from body to the ground frame. Okay, so this ground to body is just the inverse, and that is the transpose. And this, second thing, we have calculated it to be minus R transpose times T, and then this is 0, and this is 1. So that is how, you can get a geometrical interpretation of why this actually is an inverse. Okay, because in one case you're going from G to B, so you're searching for the pair R and T that takes you from G to B, and in the inverse you're searching for the pair that takes you from B to G. Okay, and that pair happens to be this RBG and TBG. Any doubt?
I have a question, sir.
Sure.
Is there any reference books or any material other than this where I can get more questions or more explanations on this topic, because it's really tricky?
Yes, sure. Because I am asking for questions because these things are actually tricky. It is
Yes.
somewhat difficult to wrap your head around. So there is a book referenced. I think it is given the references also. It is J.J. Craig, Introduction to Robotics by J.J. Craig.
Okay.
That is
J.J. Craig.
Yeah, that is a really good book for this kind of introduction kind of stuff.
Yes.
Okay, and in general it is quite a good book also.
Okay.
Okay, so I will just quickly tell you the alternate method. Should I tell the alternate method?
Yes, please.
Yeah.
Okay. Method 2, approach 2. It might take some time, but you guys asked for it. Okay, so let us say that there is some frame. Okay, let us call that A. Okay, so there is a vector V in this frame. Do you guys know about Euler's theorem?
Yes, sir. That we know. We've studied in the high school standards.
And what is that? Can you tell me?
EI theta cos theta plus I sin theta.
What?
Is it the identity e power I theta's cos theta plus I sin theta, or that's different?
No. That is the Euler's
Different.
formula.
Okay, okay.
Oh,
I'm talking about
Sir,
Euler's.
is this something related to fluid mechanics? Like you find out the um, velocity or something, like you
No.
find it with respect to space.
I think you are talking on the similar lines because it is used in fluid mechanics. Okay.
I think it's got to do with primes. I think
No,
is that
actually we are having all these different responses because Euler was a very genius kind of guy, so he worked in a lot of different fields. Okay, but the Euler's theorem that I'm referring to here is the Euler's theorem about the rotations. Okay, and what that says is that any rigid body rotation can be assumed as a rotation about a single axis by some angle. Do you get this? So basically for every
Okay, so
so basically for every
is it
rotation there is a vector, basically a unit vector and an angle that can completely define that rotation.
I have a question.
Yes.
So if you have a body in some position one and you do some 2, 3 transformations, 2, 3, 4,
Yes.
you mean to
Yes.
say there exists some axis from which I can do a single rotation from by which it goes from 1 to 4 directly?
Yes. And not the transformations. If you only rotations.
Only rotations, okay.
Yeah. This is
So
this
okay.
Euler's
There always
theorem.
exists an axis. That is what he says.
Yeah, there always exists for rotations. Okay, there always
Yeah,
exists
only for
a single axis, and a single angle. You can, yeah, of course, that can be replaced by all those rotations.
Sir, is it similar to addition of vectors?
No, no, because see, rotation matrices are not vectors. Okay,
Okay.
what it is saying is, you multiply, whatever you keep multiplying, to get your final R. This whatever rotation it is about, because see, this R1 is about X, right? Angle theta. This R2 is about Y angle theta, and so on. These might be about different axes. So this complete rotation is about some general, vector n, and about that n, the single rotation angle theta, and this will take you from R1 directly to R, basically from body to ground frame directly. So that is the Euler's theorem.
Okay, sir.
Okay. So actually, we have crossed the time quite a bit. So I will just give you, some hint on how it can be done. Plus theta s of, let us say, n cap plus sine theta s of n cap squared. I know this looks intimidating, but I do not expect you to do this. Okay, so this is called the Rodrigues formula. Okay, so what this says is, if you have n, okay, this is n actually, n that I have stated here, and if you have theta, so you can write your rotation matrix using this formula. Okay, you can look it up in Google. It is called Rodrigues formula for rotations. Okay, now using this, if you want to know about x, so you just write n as 100. Okay, and you keep theta as just whatever theta. Okay, you keep it here, and this s of n is actually the skew symmetric form of n. Do you all know about skew symmetric form? Yes or no?
I've just heard the name. I can't able to remember it, sir.
Yeah, so for
Some.
Yeah, a skew symmetric matrix is a matrix like this. Okay, so for any vector, like if I say that n is, these are the components of this vector n. So the skew symmetric form of this matrix, of this vector, is written like this. I represent it with s of n. Okay, so you use this s of n, you use this theta. Okay, you square this f, you put s of n here, you square this and you put it here, you calculate this. If you want to calculate for, you want to know for rx, you put n as this. If you want to know for ry, what should I put in?
0, 1, 0.
Yes. Okay, so you use this and then you will see that you will get the same, basic, these formulas, fundamental rotation formulas about x, y and z. So one approach is using geometry, directly, that you are actually trying to see, okay, where these vectors are going in each plane, and then you're writing. That is the geometric approach. And the other approach is a bit more mathematical. You can also derive this Rodrigues formula. It is little involving. You have to do something on. You can see the diagram. I'm not going to do that right now because we are already over time. But yes, you can use the Rodrigues formula to actually then derive the completely mathematically derive the expressions for Rx, Ry and Rz. Okay, so I think we will keep the information till this only for this lecture. I will stop presenting. And now,
Sir,
yes,
uh,
yes, yeah. I was just about
sir.
to ask. Are there any questions?
Yes, sir. This is not a technical question. I just want to apply. I was happy for this 1 hour lecture that you gave us. It was really good,
Yes,
and
thank you.
I just want to ask you that I was a student from mechanical stream who is currently going into third year, and I was not that much open about computers and programming like of things. But searching introduction to robotics in YouTube, I was I've seen more lectures on algorithms and programming. I
Yes.
was very much. I thought I don't know how I'm going to actually approach it in a way because I didn't have a basic idea of how a programming works and algorithm and how to work on it. Do I want to prepare for it in a specific manner so that I can crack this course? And I definitely want to write this course and I want to pursue a certificate in this course. So what can I do for it from the beginning itself, sir?
So see, initially it is a good thing if you are this interested that you have taken this course, because robotics in itself is a very interdisciplinary field. So you need to know basics quite well of a lot of things. Okay, so the best thing is to take a course, in my opinion. Okay, you take an online course or a course at any university or your own university if it offers a course on robotics. So the best thing is to take a course, and to get good at robotics, actually as a field, you have to apply it. So you just start making some models. I'll just quickly say one thing, that we can do this discussion after some time, but before, if there are any questions about this course itself or the lectures, because then I can stop the recording and then we can do this discussion.
Sir, I have one doubt.
Yes.
Sir, in the formula, last formula which you mentioned, Rodrigues formula,
Yes.
can you please specify once what what does R stand for and what does I stand for?
Oh, sorry, I should have said. So I is the identity matrix, 3 cross 3, and R is the rotation matrix. The
Okay.
final rotation matrix corresponding to this final rotation.
Okay.
Okay.
And sir, this n cap stands for unit vector, right?
Yes, unit vector.
Okay, sir.
Yeah, so unit vector about which the rotation is happening. Yes, this Niranjana, it will be put up on the website. Okay, yeah, sure. more questions? Are there any?
No, sir.
Okay, so if there are no more questions, then you guys can leave, and then I
Sir,
will stop the recording. Yes. So
sir,
if anybody
last,
just a minute. If anybody does not have any questions, then they can leave. Yeah. Yes.
in last we have seen about skew symmetric matrix, right, sir?
Yeah. In the end, in the Rodrigues formula, yes, S is skew
Yes.
symmetric matrix.
Then how could we use an skew symmetric matrix in that formula, sir?
Mm. Are you asking how to do it, or are you asking is it valid to use a skew symmetric matrix?
Means how to use, sir?
Oh, do you know how? Did you see the part where I explained how to write a skew symmetric matrix for any vector?
Yes, sir.
Yeah. So you write a skew symmetric matrix, and then you plug
Yes.
that matrix there. That's it.
Okay, sir.
Because that
Okay.
whole equation is a matrix equation. R is a
Yes.
matrix. I is also an identity matrix. 1
Yes, sir.
minus cos theta is a scalar.
Yes, sir.
Multiplied by S. Now S is a matrix.
Yes, sir.
And then in the next term, sin theta is a scalar. But then S square is also a matrix.
Yes, sir.
So it is a matrix equation.
Okay.
Okay. So I will stop the recording now. If anybody does not have doubts related to this course, they can leave. Thank you.